Hi. So, in the last discussion, we basically showed that the hydrostatic model of the solar corona, or more generally, the corona of any star, cannot be valid only because it gives us a pressure which is non-zero and considerable at infinity. Okay. Now, it basically led to think people that the corona is not hydrostatically stable. Okay, so that means that corona is dynamic and it's a flow, right? It's flowing. And after that, various spacecrafts they showed that the spacecraft measured the by in situ measurements. Finally, nowadays we understand that the coronal plasma and the coronal fluid is basically expanding, okay, outward in the radially outward direction from the sun, okay, almost in an isotropic way, almost, okay. There is a small anisotropy due to magnetic field, that's true, but almost in an isotropic way. And this is known as the so-called stellar wind, okay. And for sun we talk about solar wind correspondingly, okay. So in this lecture we will discuss this stellar wind or solar wind. So now Parker was the first one who concluded that the solar corona, or the just a minute, yeah, the solar corona or the corona of any star cannot be kept in hydrostatic equilibrium only by the interplay of gravity and hydrostatic pressure. Okay. Or in an alternative way, one can say that the corona of a star can be in hydrostatic equilibrium only if there is something to account for a finite pressure at infinity. And we all know that in reality, the pressure at infinity should be very small unless there is some agent to account for the pressure. Okay, so infinity means that there is no mass, there is no plasma. Ideally, of course, if there is a source which is a distant source, okay, that is also sometimes possible, that we will come at the very end of this discussion. Okay, then it is possible. Now, in general, the pressure at infinity is quite small, and actually it's very near to zero. Okay, and then the fluid or the plasma of the corona expands in outer space, and this is known as the stellar wind or solar wind, I just said. Okay, so in the year 1958, Parker predicted for the first time this coronal outflow in the form of solar wind. Okay, but the model with which he started his work was a very simplified model, and the model nowadays, with respect to today's consideration, the model has, one or two things which are not completely correct. But yet, this, even with this very simplified model, Parker reached to a number of important conclusions, okay, that we will discuss. So the basic assumptions of Parker's model was, of course, a steady spherical flow in radially outward direction of the coronal plasma. Okay. Although he realized very well that this is a plasma, this is an ionized, charged, fluid with charged particles or ionized particles. So ions, electrons will be there mostly. But as a first approximation, he assumed his model to be constituted of neutral fluids. Okay, and that's why we are talking in this context. Otherwise, I would have talked about this after introducing plasma and the plasma fluids. Okay, and finally, he said that we don't have to think about the energy equation because we will assume a simplified isothermal closure for the solar wind. And this is also not a very good approximation for the solar wind, because the coronal plasma, because most of the cases the temperature is not constant. So some people do it with polytropic closure, okay, that is somehow much more closer to reality than isothermal one, but he did this just to start off, okay. So polytropic closure means T is constant, so P is nothing but kBT by M, okay, times rho. So this is another way of writing. So rho by M is N, so N kBT. So P is equal to N kBT. And if you write in this way, then kBT by M all are constants for an isothermal case. So you can say this is a constant times rho. So pressure should be proportional to density in an isothermal fluid. And the proportionality constant, you can easily remember what is this. This is nothing but kBT by M, which is equal to the sound speed square. So already people knew about the sound speed in a medium. So we all know that for a medium, I will also come into the detailed derivation of sound wave for compressible fluids. But much before that, people used to know that sound wave is produced by the pressure and density variation of a compressible fluid, and dp by d rho, okay, is given, gives the sound wave speed, okay. Mostly, this gives the square of the sound wave speed, to be precise. And for a isothermal case, dp by d rho is nothing but p by rho, and which is equal to c square. But only for isothermal case, your sound speed is a constant. For polytropic fluid, non-isothermal polytropic fluid, this is no longer true. Okay, so this is sound speed square. Okay. Now, the governing equations we can now written in this way. So first of all, we said this is steady flow. So that means all the del T will go away. And so this is the continuity residual part of the continuity equation. Divergence of rho v is equal to 0. Now, when we are talking about a spherical symmetric case with only radially outward flow, then this will be, the divergence will be written in a spherically symmetric way, and the only non-vanishing velocity will be the radial part of the velocity. So let's say here, basically when we write this, we assume that v is nothing but v r cap. Okay, so I am not saying anything like vr, I am simply saying this is v r cap. Okay, for simplicity. If you do that, finally you can show that r squared times rho v is a constant of the flow. Okay, then if you differentiate both sides with respect to r, okay, so now these things are the function of r only, so del or d, they are both the same. So now you differentiate both sides with respect to r, and you will have 2 times r rho v plus r square d rho dr times v plus r square rho times dv dr, that is equal to 0. Okay, and then again dividing the whole thing by r square rho v. Of course, here we should assume that r square rho v is never equal to 0. Okay, then you can say that this is the final equation comes to be 2 by r plus 1 by rho dr plus 1 by v dv dr is equal to 0. Okay, now this is the residual part of the momentum equation for spherically symmetric case, steady flow. So del v del t, del rho v del t is going away, or rather it should be rho times del v del t, which is now 0, because anything del t is 0. And this part we have to write in spherical coordinates. So this will simply be rho v dv dr. Okay, because only the radial component of velocity survives. Gradient of p is dp dr. Okay, so minus dp dr, And what about this one? So this one is simply minus gm solar by r square. Again, we are assuming that the coronal plasma is inside the gravitational field of the sun, whole sun. Okay, I mean, excluding the mass of the solar plasma if you want, because it in any case does not, I mean, sorry, coronal plasma. In any case, the addition or subtraction of the coronal plasma doesn't change much to the solar mass. Okay. So, that is something to know also, that, I mean, so it is good that if you search the rough ratio of the coronal plasma mass in general and the total solar mass, then it will be clear. Okay. Then finally, you can just write just substituting P by Cs square times rho, this equation. Okay. There is no other change other than this substituting P by Cs square rho. And Cs is a constant of the system. So we can simply write this equation number 2. Now we can actually divide the whole thing of 2 by 1 by r, and I mean actually divide by Cs square by rho, not 1 by r, Cs square by rho, so that this term will then be equal to 1 by rho d rho dr, and then you have 1 by rho d rho dr, and then you you equate these two expressions of d rho dr, and if you do that perfectly, so check at home, you should obtain this. 2 Cs square by r plus Cs square by v dv dr is equal to v dv dr plus gm solar by r square. Okay, which after simplification comes out to be v minus Cs square by v times dv dr is equal to 2 Cs square by r minus gm solar r square. Okay, so these two terms. Okay, so this is the term related to the velocity gradient. Okay, now in this total equation, okay, so this is the Parker's equation for the isothermal solar wind, considering this as a steady flow. This is the this is the flow equation. So this is a steady flow. So but velocity is non-zero, so velocity should have a gradient with respect to the radial coordinates, right? Now you can, it is a very good exercise, you can do at home yourself. If you are blocked, then I can help, or you can search over internet for the other literatures, that what will be the modified version of this equation if instead of an isothermal fluid you take a polytropic fluid. Remember, at that point Cs square is no longer a constant of the system. Okay, so do that. Okay, so I am not saying that you must get a different form. Maybe you get a similar form or a different form. Just do it yourself and let me know. Okay, if you don't do the exercises, then this will be difficult to follow these things. Okay, so it is really recommended that you do the exercises, small exercises, which I suggest you during the lectures. Okay, now when you see in this total equation, you can simply see that this term is 0 when V is equal to Cs. Then this term should also be 0, and that gives us a specific value of the radius, which is called the RC, that is critical radius. Sometimes people also say sonic radius, because this is the radius at which the flow velocity is just equal to the isothermal sound speed. Okay, and that is equal to gm solar by 2 sound speed square. So what is the meaning of that? The meaning is that, so Parker thought that the solar wind basically, after getting originated from the coronal flow, okay, coronal the solar corona, when it expands, first it starts with a very small velocity, then it achieves the sound speed, okay, at this critical radius or sonic radius, and after that it becomes supersonic. Okay, of course, when we talk about supersonic or subsonic, all are with respect to the isothermal sound speed. Okay, but in general, whether this is really supersonic or subsonic, you have to do with a proper polytropic closure. Okay, but okay, so that is another thing. So you can do that for fun. Now here for Parker's model, in this course I will just discuss Parker's model, which is based on isothermal closure. So you can see that this is the critical radius which changes the nature of the solar wind from subsonic to supersonic. That was the Parker's initial conjecture somehow, that solar wind is getting solar wind is getting energy somehow, and then it accelerates, and when it accelerates it gets energy further. The speed of it of course should increase. So what is really the reason of the acceleration? This is another question which maybe we should come when we will discuss about turbulence. But at this point, just think that it's a somehow very reasonable consideration that the solar wind basically accelerates after generation. So this is much reasonable to see that the velocity first start to be less than Cs, then reaches Cs, and then overshoots Cs. Okay. Now finally, you have this relation, this one, and but how to do that? Now you have to just integrate V to see the solution of this whole problem. So V will be finally, in the final equation, V will be a function of R, and that's what we have to find. So if you do that correctly, okay, one bonus is Cs is your constant. You will see the solution is given like this. V by Cs square minus logarithm of V by Cs square is equal to 4 times log R by RC plus 2g m solar by RCS square plus the constant of integration C0. And this V by Cs is known as Mach number. Okay, so that is a vocabulary I expect all of you know. So if Mach number is greater than 1, the flow is supersonic. If it is equal to 1, this is called transonic or sonic. And if it is less than 1, then it is called subsonic. Okay. So then you can simply plot, okay, the Mach number with this dimensionless number R by RC. So Mach number is also a dimensionless number, and you will see that this type of equation actually permits 6 type of solutions. So these are all denoted by 1, 2, 3, 4, 5, 6. Okay. So now which solution to take? Okay. Now solution 1 and 2, they have a problem. So this is the solution number 1. If you see this 1 and 2, they are actually double valued. So that means for a given value of R by RC, or that is a given value of R, you can actually have 2 possible values of corresponding solar wind speed, and that is not possible. This is unphysical. That is not possible. Okay. So that's why these two are not accepted physically. Now solution 3 is this one, which says that the solar wind is always supersonic because Mach number is greater than 1. So this is the sonic line. And this one, so 4, says the solar wind is subsonic always. Okay. Now solar wind, it is true that, well, there are other considerations by which one can actually show that there are evidences. One, of course, from the spacecraft data, that solar wind starts being subsonic. That is just by calculating the initial coronal temperature and this type of thing. Okay. So if it starts being subsonic, then there are 2 possibilities. Either it becomes supersonic after a certain region, or it retains subsonic, right? So in any case, 3 is not possible. Now 4 may or may not be possible, But once again, then the Parker's consideration says that solar wind. So 4 is also not a, I mean, is a valid solution for solar wind. Okay. So this is called the breeze solution. Okay, breeze solution. Now, uh, just to write, maybe this is called a breeze solution. Breeze. Okay. Now, Parker considered solar wind to start with small velocity and then accelerates thereafter. And that is why, finally, for Parker's problem, solution 5 is the most appropriate, because if you see 5, it starts being subsonic and finally gets supersonic. And this is the sonic radius or critical radius, and that's exactly, that means r is equal to rc, that is r by rc is equal to 1. Okay, and why not 6? 6 is something where the wind decelerates. Actually, it starts being supersonic and it then becomes subsonic, which is not also possible. Okay, now after that, just calculating the, observed values, just fitting the observed values with this solution, one can actually show that the realistic values of the solar wind speed basically matches closely when C0, or the constant of integration, is nearly equal to -3. Okay, so this is also my question to you. When you will do the polytropic case, then just think and do, okay, is the conclusion same for polytropic case? That means also if there are these 6 type of solutions and you have also one type of solution which is the perfect and the other not, okay, is the same story continues, does the same story continue there, or this is a different story? So that's the research part. Okay, so something I will do here, but you have to think a bit, beyond what is done in the lecture. Okay. Now finally, there is another thing. So finally we can see that even with this simplistic neutral fluid, spherical, steady, isothermal consideration, Parker's model was powerful to at least give the nature of the solar wind in a very simplified, in a, yeah, how to say, as a first approximation. Okay, so this was not bad. At least the transition from subsonic to supersonic becomes here. Now from equation 1, 2 and 3, so we should go back to equation 1, 2 and 3. So 1, 2 and 3. So if you carefully see, actually 1 and 2 makes 3, so I just checked 3. That if V is a solution of the problem, then minus V is also a solution. Okay, because in this term there is V dV, so minus V will not affect. Here you have 1 by V dV, also there will be no effect of minus V. So that means that if this is a this equation is the equation for some plasma which is flowing outward, that can also be the equation of a problem where some plasma or some material is coming spherically inward, and this is nothing but the popular problem of spherical accretion, which was addressed by Bondi in the year 1952. So accretion, mass accretion in astrophysics is a very deep problem, and at that time people started, so they found some observational evidences of mass accretion, but they did not know how to proceed analytically, and Bondi started by very simplistic model of spherical accretion, and then finally it was shown that this model of stellar wind, the equation of stellar wind and the equation of spherical accretion, they're exactly same when we talk about the steady condition. Of course, if the condition is not steady, then they are not equal, because del V del T term when it comes, then V and minus V makes a difference. Okay, but for steady case, spherical accretion problem and stellar wind problem is the same thing, just for the opposite direction. Okay. So in the problem of spherical accretion, it is assumed that the accreted mass starts with a small subsonic speed at infinity. So that means at very large distance there is a source of some mass. For example, let's say some star comes in the rather starts to come in the neighborhood of another star. So when it starts to come, so it was at the large distance and then it comes really closer. Okay. So it simply says that some mass is there actually at a large distance, which is theoretically at infinity. Okay, and that mass starts with a small subsonic speed. So if you see that the schematic figure is like that. Let's say I have some star or something like that, and let's say I have not a star or something, but just an idealistic approximation. I have a mass source which is isotropically distributed, okay, around this star. Okay, and from this mass source, mass is coming isotropically inside, okay, to accrete to this star. Okay, so then with respect to this star at very large distance, okay, if it starts from very large distance from the star, you can say that there is a source of mass and actually source of pressure at infinity. So in that case, actually infinity pressure at infinity will be, something considerably bigger, and then it basically leads to an inward flow. Okay, so again the flow will be from higher pressure to the lower pressure region. Okay, as we all know. So this is the problem of spherical accretion, of course, which starts with subsonic speed at infinity, but finally accelerates to supersonic speed close to the center of the accretion. So now you see it starts with subsonic speed at infinity, and so here for example this one, and then it accelerates to have supersonic speed at very close to r is equal to 0, and that simply says that solution number 6 will be an appropriate solution for this Bondi's spherical accretion problem. Okay, this problem is also called Bondi's problem. Okay, now however, as I said, that this was just a first way out to address the accretion problem in astrophysics theoretically, but spherical accretion does not represent the reality. And actually it is interesting only for academic purpose, because to show that correspondence between this one and the stellar wind problem at steady state, the equivalence between the two. Okay, but in real accretion, the mass gets accreted in the form of a disk, okay, which basically becomes, because you have a star and another star comes, and then it's there's a star and another, so it's a very dense and small star is at the center, and the less dense star, less massive star, but the bigger, with a bigger volume comes, and then it starts to leave mass, and this mass with an angular velocity actually starts accreting this mass in the form of a disk. Okay, and that is the famous accretion disk of astrophysics. Okay, and that is exactly our next topic. Okay, thank you very much.